All right, guys. So without further ado, we did talk about the last two of the ideal basic circuit elements, the inductor and the capacitor. And what I really want to do now is derive the LV characteristics of the capacitor. We're going to take a closer look at this. Hopefully, you've seen this element previously in your physics classes. We will be relying a little bit on that as well. And I want to start off by taking a look at a specific model of capacitors. Capacitors come in many different shapes and sizes, but we're actually going to take a look at one type of capacitor that's extremely common in particular. We're going to get a mathematical relationship between the voltage across its terminals and the charge that accumulates on the capacitor. And then we're going to generalize that and take a look at how that fits into our circuit analysis. Right. So without further ado, let's actually start talking about the capacitor. And our next will be the parallel plate capacitor. Sneaking an I in there. Let's try that again. Okay. The picture looks like the following. So we have a top plate that's made out of a metal, some sort of conductor. And we also have, on the bottom, we have another plate that's made out of a metal as well. Right. However, in between the two plates here, we actually have a bit of material, and this material is what they call the dielectric material. Now, dielectric is just a very, very fancy way of saying an insulator, right? So the basic idea is that with the insulating material, you cannot have charges that are passing from the top plate through the insulating material down to the bottom. So this is an insulator. Now, the insulator itself is characterized by one parameter called the permittivity. And for the insulator, this is usually denoted with the Greek letter epsilon. On top of that, the capacitor itself does have a certain set of dimensions. The thickness of the insulator right here is D. The top plate and the bottom plate both have the same length F. And there's both of these actually share in common like this. Now, one of the things that we can do is we can attach to both the top and the bottom plates some wires and place a voltage across the plates themselves. Now, one of the things that can be shown, and this is where I'm going to rely on a little bit of physics knowledge, is that if the distance between the plates, the thickness of the insulator is much, much smaller than either the length then the capacitance is approximately permittivity of the insulator, the cross-sectional area of the plates, divided by thickness of the insulator. In other words, this is epsilon, the length times the width, by d. Now, there are a few things here that are worth actually mentioning. The epsilon right here is, again, the permittivity of the insulator. It's something that you can actually look up on a table. And in general, if you were to look at permittivities for various materials, you might not actually find the epsilon for the insulator. What you're actually going to find is what we call the relative permittivity. Okay. The relative permittivity itself, so this little 3 equal sign line means by definition, is the relative permittivity. Um, And it's this that you can actually look up in materials. So this is what you can look up in tables, usually. This is actually being multiplied by another constant of nature, epsilon naught. This right here is the permittivity of free space. And the actual SI value for the permittivity of free space is 8.854 times 10 to the minus 12 farads per meter. Now let's talk a little bit about how this capacitor actually works. Right. Now, if I actually go to my capacitor and actually place across the two terminals, so notice that I have the top terminal, I have the bottom terminal. If I actually place a voltage across these terminals, then one of the things that's going to end up happening, so here there's a voltage between the top plate and the bottom plate, is that it's going to be a certain amount of charge that accumulates on the top plate. Now, that charge is not allowed to flow through the insulator, right? But there is a Coulomb replacement, right? Between positive charges that are accumulating on the top plate and the positive charges that are on the bottom plate. The bottom plate initially is neutral, and it's going to push those charges away, and what's actually going to be left here on the bottom plate is an equal but opposite number of negative charges. So what you actually have is you don't have a current that's flowing through the insulator, but what you actually have is what they call a displacement current. And it really has to do with the Coulomb repulsion between unlike charges. Right, so keep in mind that's how a capacitor actually works. Right. Now, the most important property of these capacitors is that the voltage is proportional to the charge separated. In particular, one thing that you can say is that the proportionality constant between the voltage across the plates and the charge that has accumulated on the plate is what we call capacitance. But here, the proportionality constant is what we call capacitance. We use the letter C, capital C, to denote it. Now, notice that this can actually be encoded in equation form. So, here in the equation, the charge on the plates is equal to the capacitance times the voltage. Right. So, let me make a very quick change here. On top here, we have plus Q, and on the bottom plate here, we have minus Q that's accumulated. Like so. Right. Now, we're introducing a new quantity, the capacitance. And let's make mention of the fact that this has units. So the units of capacitance, well, just based on the SI units for charge as well as voltage, we can see that this is a Coulomb per volt. This is also an ampere times second per volt. This has a more common name. This is a farad. Now, keep in mind that farads are huge quantities. In general, capacitors will have a capacitance on the order of either nanofarads or even picofarads in general, right? So that's 10 to the negative 9 farads or 10 to the negative 12 farads. If you were to talk about something that has a capacitance of a farad, right? So 1 farad, 2 farads, 3 farads, it would probably take up a room. It's a huge unit, tremendously large, right? Now, one thing that's also fair to say is that anytime we introduce a new element, whether it be resistor, voltage source, or current source, or whatever it might be, we need to find the IV characteristics. Right. So here, the rest of the time is going to be used in finding the current voltage characteristics. Before we do that, let's actually generalize, move away from the parallel plate capacitor, and let's talk about the capacitor in the context of circuit analysis. There is a schematic symbol that we use for the capacitor. It looks like this. Now, the reason I talked about the parallel plate capacitor is because the symbol itself looks like the parallel plate capacitor, right? So it's best to talk about that one. Now, it is characterized by capacitance C, and again, remember that it is a passive element. So over here, if I have a voltage applied across the capacitor terminals like this, then we have no other choice. The current must flow from high voltage down to low voltage. Now, in terms of the IV characteristics, we're actually going to look at the defining feature, right? So here, the equation that we just wrote a second ago is this one. I'm going to go ahead and call this equation 1. So if I actually start with equation 1, in other words, the charge on the plate is equal to the capacitance times V. Then one of the things that I can do is I can actually take the time derivative. So here, if I differentiate both sides with respect to time, this, right? Hopefully you recognize on the left-hand side, well, that's the current that flows through the capacitor. So here, the current that's flowing through this, by definition, is dq dt. On the opposite side, we have to be a little bit careful. The reason we have to be a little bit careful is because here, on the opposite side, on the right-hand side, it's a part of capacitance times the voltage. Right? Now, if you actually take a look at what the capacitance depends on, so let's go back up to the equations that we have here. Notice that the capacitance only depends on the insulating material as well as the geometric properties of the capacitor. So if, let's say, the separation between the plates is not changing, if the length and the width of the capacitor is not changing, if the dimensions of the capacitor are not changing, and you're not trading in or out, let's say, insulating materials or anything like that, then C is constant. It doesn't have to be. If the properties of the capacitor are not changing, then one of the things that we can do is on this side, we can replace this with I, and we can actually push C through the derivative. And what we're left with is this right here. This is where I wanted to get to. Notice that it is the relationship between the voltage and the current. It is a differential equation. Now, this is the IV characteristic. This is in differential form. Like so. And notice that we are respecting the passive sign convention. We actually gone up to this capacitor, and had we actually defined our voltage and current, like so, right, then it wouldn't be this equation that relates the voltage to the current. You would have to actually input a minus sign into them. Right, so you have to put those in by hand every single time. Right. Now, this is in differential form. One of the things that we can do is we can invert this into integral form. So if I were to multiply both sides here by dt, and then integrate like this, over here I'm integrating with respect to time. So I'm going to go from some initial time t naught to some final time t. Over here, I would be integrating with respect to the voltage. So here at some initial voltage, this would be some final voltage, like so. Notice that I can also move the capacitance to the opposite side just by dividing. So this equation I can rewrite in the following manner. So I, which is generally a function of time, like this. Capacitance is constant, so I can put that like this. I have V naught times dV prime. And here there's kind of an implicit 1, so I can actually integrate that. In which case I can rearrange this in the following manner. I'm going to move this C, the opposite side, by dividing both sides by the capacitance. And on this side, I actually have the integral of V prime evaluated at the top down, which is my voltage as a function of time, and then bottom line, it's my voltage at time equals 0. So here, on this side, when I subtract the two, I have V times V naught. I can add this term to both sides, in which case I get that V, which is a function of time, is 1 over the capacitance, the integral from some initial time to some final time, and the current integrated with respect to time, plus whatever voltage existed at time t equals 0. This was the equation that I wanted to arrive at. This is the IV characteristics. This is an integral form. Now keep in mind that both the IV characteristics in differential form and in integral form, they contain the same information, but depending on the problem that you're trying to solve, you might want to use one or the other, right? But keep in mind that they contain the same information, right? This is enough for capacitors. We will explore capacitors a little bit more in detail in the next few videos.